Hi everyone. In the previous classes, we have seen the concept of adders, subtraction, and multiplication, right? So in this multiplication also, we have seen both the signed number multiplication as well as unsigned number multiplication that we did with the help of Booth's algorithm, right? Yes. So guys, these are the operations that are comes under arithmetic circuits. This is what I said, right? These arithmetic circuits are comes under combinational circuits. Am I right? So this is where we started the concept. Why I am going to call these are also as combinational circuits means these are just going to produce the output by just taking the present input. That is what we can observe from the given examples, right? Yes. So this is one kind of example, and also we have seen the examples, right? So we can able to convert one code to another kind of code like this we have seen, right? So if you are able to observe here in adders, we discussed half adder, full adder, binary adder, or I can call it as a triple carry adder, okay, or I can call it as a parallel adder. Then I have seen the concept of carry look ahead adder, right? So if you are going to say about binary adder, which is going to take two binary numbers and it is going to perform its addition, am I right? Say for example, if you are going to have two numbers 1001 as input and the other number like 0110 as input, which is going to produce the four ones as your output. That is what the binary adder is going to perform. Coming to carry look ahead adder, which is also going to perform the same operation, but with an advantage that it's having less propagation delay compared to binary adder, right? Yes. And this same binary number addition we can able to get with help of another kind of where we try to discuss about the concept of subtraction, right? Meaning that we can able to get the same addition as well as subtraction with help of a single circuit. That is what I can say that as 4-bit binary adder or subtractor. So I can able to perform binary number addition either purely through binary number circuit, or I can able to go through 4-bit adder or subtractor. Okay, fine. See guys, the reason why I am trying to make stress this one is now I am trying to perform BCD addition. BCD addition. Now try to think, if I am going to give two inputs, one input is BCD, another input is also BCD, another input also BCD, right? For example, let me take the one input is A0, A1, A2, A3, right? BCD means what, you know, right? Every number is going to have the range from 0 to 9, which is going to take 4 bits, right? That's why I have taken 4 bits. Similarly, BCD, another number B0, B1, B2, B3. Yes. Now, in order to perform addition of these two BCD numbers, we can able to either use BCD adder or we can able to use simply 4-bit adder or subtractor, right? So when you are going to use 4-bit adder or subtractor, you can simply pass. See, I have taken this one from the previous classes. See, observe here this 4-bit binary adder subtractor. You are going to simply pass m value as 0. When you are going to pass the m value as 0, then the circuit will act as a adder. M value as 1, then the circuit will act as a subtractor, right? So now what you can do now, so B as a valid data and A as a valid BCD data, right? The same circuit I can able to redraw, right? So sometimes you can able to observe in some kind of textbooks what they did now, instead of writing this much complex diagram, they will simply write as 4-bit adder or subtractor. And for this internal logic is there. For this they are going to give the inputs a0, a1, a2 and a3, right? As I have given here a0, a1, a2 and a3 directly. Okay. And how the other numbers are going to be given? By simply passing through XOR gate. So here there will be an XOR gate. There will be an XOR gate. So how many XOR gates are required? 4 XOR gates are required. Guys, don't worry about the diagram here. Diagram may look ugly. Yeah, here so I am trying to redraw this one, right? B3, B2, B1 and B0. For this they are trying to pass one external input. That input will be connected like this, right? So I can say that this has m. When m equal to 0, when m equal to 0, I can say that this circuit will act as a adder, right? So the same input I am going to give as C0 as input. Okay, and when this m value as 1, it will act as a subtractor, and finally it is going to produce the carry. Carry is C. Okay, so the result will get as S0, S1, S2, S3. Guys, this is the alternative way of representation of this 4-bit binary adder or subtractor. Okay, fine. Now I can design this BCD addition using either binary adder or through 4-bit adder or subtractor. You can do that. That's all up to your wish. Because when you pass m equal to 0, it is going to be act as a adder. M equal to 1, it will be act as a subtractor. Okay. For time being, I will try to do it with the I'm trying to think which way I can able to easily represent. Okay, okay. Let me do it with the binary adder, 4-bit binary adder, meaning that which is going to take two 4-bit numbers and it's going to produce some result, right? So it is going to produce the results as S0, S1, S2 and S3, right? Guys, as I am saying that this is a 4-bit adder which is going to take some C0 add as input, external side. Yes. Now I am going to simply passing these values. Okay, so this is what the basic thing what you can understand easily, right? Yes. Now you have to understand one thing. When you are going to add two BCD numbers, like for example 1 0 0 0 0 0 and the another number is 0001. If you are going to add, you are going to get 1001. What is the value of 1001? It's a 9. So 9 is in actual range, so it is valid. So this kind of output is valid. But if you are going to take something like this 100 0010, what you are going to get? You are going to get as 1010, which is 10, which is not a valid BCD, Then how we are going to do that, right? So definitely your answer will may get in this range also. Am I right or not? Yes. So guys, when you can say that the result S3, S2, S1, S0 as invalid, when I can say that the combination of S3, S2, S1, S0 decimal value is greater than 9, I can say that invalid. Right? For that, I need to construct a circuit. Right? So if I would like to construct a circuit, so I will try to take those inputs only: S3, S2, S1, S0. Okay, fine. So we'll do certain kind of function. Okay, so what are the possible values that you are going to get as invalid? So one number is definitely 1010. So 1001 is 9, which is invalid. So when you are going to take 1010, it is invalid, right? So for that case I am going to construct the circuit, and for this case also invalid, excuse me, invalid, and similarly 101 invalid, 1110 invalid, 1111 is also invalid, meaning that for all these cases, you can say that your output is invalid. When you are saying that your output is invalid, what you are trying to do, ma? You are trying to simply add plus 6. You are simply adding plus 6. So means that for this particular result, S3, S2, S1, S0, you have to add a 6 number, right? 6 number, how can you write? Can I write like 0110 in the form of 4 bits? Yes. So if you would like to add 6 to this S3, S2, S0, you have to require one more add. Am I right? Yes. So now I will try to take one more 4-bit binary adder, right? If I am going to give 4-bit adder again for this circuit, and I need to produce compulsory here what values? Here you have to give the values as 0110, so that this 0110 means what? 6, and will be added to this one, which is going to produce the result as R0, R1, R2 and R3. But the point here is you need to activate this circuit, meaning that this input 0110 should be given from external side, right? Otherwise what will happen? Each and every time when you are going to get the result, it is going to simply add the plus 6 and it is going to produce the output. That's the reason. For what combinations you are going to get invalid, based on that, meaning that based on that cases, I am going to activate this circuit. How can you do that? Means, see guys, when you know, when you construct the truth table, can we able to solve the expression for this? Yes. Let me try to take. Okay, fine. So for our simplification, uh, I can take as S3, S2, S1, S0, right? Because the order in which I have written the truth table, that will be easy for us to read, right? So this will be 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. Okay, fine. What are these values, guys? I think this is from 10 to 15, right? 10 means what? So I think these two lines will cover up to 7, and this will be 8, 9, 10. I'm going to write it as 1. Like instead I can write in the red color, but 10, 11, 12, 13, 14 and 15. Okay, fine. These are the ones, right? So now can we able to minimize this one? Yes, we can simply minimize this one by making a combining of these four as one and these four as one, right? If you are going to solve this one, you will get as S3, S2, S3, S2, and these four combining, you are going to get as, I think, S3 is one combination which is not changing, and S1 which is not changing. Okay, fine. So means with the help of this Boolean truth table, I am going to get a function as S3, S1 plus S3, S2 plus S3, meaning that if I am going to have S3, S1 will yield to 1, or S3, S2 will yield to 1, I need to activate the circuit, right? Yes. So what I can do now, I will try to draw the circuit. S3 and your S1. S1. So I will get one AND gate, and S3, S2. One more S3, and I extended this one, and this one is S2. This one is S2. Okay guys, so when you are going to get either of this as activated, definitely you need to activate this circuit, meaning that that value you have to give it as input to this one, right? If you are going to give these two as 1, see, meaning that it is going to produce here output as 1, that output will be passed to this one, right? So if you are going to pass there as 1, what about these two? These two are automatically 0 only, because we are not passing anything. Okay, this is the one case. So when this circuit is activated, it is going to produce respective results. Okay guys, and when you are going to add plus 6, again it may generate a carry also, am I right? So if you remember the BCD addition, it may generate a carry also. So generating a carry also is also making a invalid data. So that's the reason what you can do now, you can simply take the carry also will be an invalid data. So or carry like C4, meaning that, so with respect to this one, so the final function for uh, to to activate the second 4-bit binary adder is S3 S1 or S3 S2 or C4. Okay, fine. So now try to observe, if you are going to take simple example, whatever it may be. For example, let us take 1001. Sorry, I am trying to take here as 1000, and here I am trying to take as 0001, right? So when you are going to do this one, your result will be here as 1001, 1001, right? The same thing is going to pass, right? So here this particular circuit defines as S3 S1, this particular defines as S3 S2. Is there any carry here? Then no carry, that is 0. And what about S3 S1? S3 S1 is 0. What about S3 S2? Is again 0, right? All are zeros. When all are zeros, it is going to produce 0. So here it is going to produce 0 0, right? When all four zeros are there, 4 zeros plus 1001, 4 zeros plus 1001, again you are going to get the result as 1001. Okay, fine. Now let's try to take another case. Okay, so as 1 0 0 0 0 10, right? So 1 0 0 0 10, you are going to get as 1010. Now C4 is obviously 0 only, because there is no carry. What about S3 S1? S3 is this one, S1 is 1. 1 and 1 is what? Here you are going to get 1. When in the OR gate, if at least 1 is 1, here it is going to pass 1 1. So 0 is going to be activated. Then 1010 plus 0 is going to be added. Then you are going to get the result. As if you are going to do it 0, let me do here, instead of getting 1010 0 you are going to get 0. This will be 1 is 10, 1 is 10, 1 is 10, right? This is the way. So you are going to get here all 4 zeros. This is for what? BCD adder for one digit. Okay. I hope you understood this clearly. Thank you.